Welcome to Lecture 14, where we are going to begin discussing Unit 4. The topic of Unit 4 has to do with momentum, or to be more specific, linear momentum. Linear momentum is a vector quantity which has to do with both the mass and the velocity of an object. And as a vector quantity, it's going to point in the same direction as the velocity vector. So this might remind you a little bit of kinetic energy, because remember that kinetic energy is 1/2 mv squared. So the difference here is that kinetic energy was a scalar quantity and depended upon the velocity squared, whereas the momentum is a vector quantity and only depends upon the velocity to the first power. So we can figure out what the units of momentum are going to be by looking at this definition of linear momentum, mass times velocity. And so that's going to tell us that the units have to be a kilogram times a meter per second. Another way of writing that is a Newton times a second. I'll leave it as an exercise to you to show that these two are equal to one another. But more importantly, this Newton times a second, this implies some sort of connection with force and time. So a force times a time is what the units of Newton times a second tell us. So is force times time a thing? And if so, how does it relate to this idea of momentum? Well, force times time is a thing. In fact, we call that thing impulse. Impulse tells us how a force will act on an object during the course of some time. We have to look at the net force over that interval of time. And so if the force is not constant over that period of time, then we will have to perform an integral in order to do so. So another way of thinking about this is if I draw a force times time graph, then the impulse will be the area underneath this curve. And so what does this impulse then have to do with momentum? Well, there's a theorem called the impulse momentum theorem, which tells us that the impulse is going to be equal to the change of momentum. And so this is something that might strike us as a little bit familiar, in the sense that we've already met another kind of theorem that had to do with a quantity equaling a change of a quantity, and that was the work energy theorem, which told us that the work on an object is going to equal its change of kinetic energy. Likewise, the impulse on the object will equal its change of momentum. And there are some similarities between momentum and kinetic energy, as we just discussed. The difference being between these two theorems, although they both involve the net force on an object, is whether or not we're looking at that force acting throughout a period of time or throughout a displacement or a distance. And so if you are attempting to solve a problem and it's unclear whether you should use the impulse momentum theorem or the work energy theorem, then the crucial question becomes, does the problem refer to the distance over which a force was applied or the time over which a force is applied? And from that you can deduce which one of these things to use. Okay, so I want to go back for 1 second here and discuss the definition of momentum having to do with both the mass and the velocity. So I can have more momentum by having a more massive object compared to, say, this rocket compared to this rocket, or a faster velocity. Perhaps this rocket is actually moving faster than that one. Okay, so when we are thinking about the impulse momentum theorem, and the work energy theorem, again, we have to think about which is going to apply to a certain problem that we might be faced with. So in this particular example, we're considering two different cars, one of which is more massive than the other, but traveling more slowly than the less massive car. And what we wish to know is which car is going to take longer to come to a stop. So we can ask ourselves, is this a work energy or an impulse momentum type of application? We're looking for something about time given a certain amount of force. And so that should make us think about impulse momentum, since that is where we bring the time dependence in. Okay, so let's go about solving this problem. First of all, let's ask ourselves which car requires the most time. Let's ask ourselves what that impulse or change of momentum is going to be. So if I set this impulse equal to the change of momentum, I know that they are coming to a stop. So the final momentum minus the initial momentum is what I mean by change of momentum. And in the final state, the momentum is going to be equal to 0. That's going to be true for car A and for car B. So for car A, you're going to have a change of momentum in the final state, 0, minus the initial velocity, where this is our velocity here, and this is our mass. Now, by definition, that impulse is equal to the force times the time. So this change of momentum then should be equal to the force times the time that it takes car A to come to a rest. Meanwhile, car B is going to give us a similar equation. This time we're going to use the mass of car B and the velocity of car B. And we're going to set that equal to force times the time that it takes B to stop. Notice that these forces do not have a subscript because we are told that they are subjected to the same amount of force. So I can divide one of these equations by the other. Putting these two together then, I can now simplify this problem. These minus signs cancel, these forces cancel, and I can plug in the masses and velocities I was given, and lo and behold, when I do that, I find that the ratio of time that it takes A to stop compared to time that it takes B to stop is equal to 1, which means that both cars actually, in this case, require the same amount of time to come to a stop. So let's ask a different question. Now we're wondering about the distance it takes for the cars to come to a stop. Distance that the force applies to the car, the force applies over a certain distance should get us to think about the work kinetic energy theorem rather than the impulse momentum theorem. So this is telling us that the force acting over a distance will be equal to the change of kinetic energy. So we can take a similar approach here. The final state of the kinetic energy is 0 in both cases, and when we divide the equations, just as we did in the impulse momentum theorem, we will have something like this on the left-hand side, and something like this on the right-hand side. The forces again cancel. These halves will also cancel. And when I plug in the numbers here, I find that the distance A divided by distance B is equal to 2/3. So that's saying that it only takes car A 2/3 the distance that it takes car B to come to a stop, meaning that car B requires more distance in order to come to a stop. Okay, so we've talked a bit about comparing momentum and kinetic energy. If I think about the magnitude of the momentum and I actually square that quantity, I can come up with some relationship between kinetic energy and momentum that you see here in this orange box. So let's imagine these two cars again and ask ourselves about the instant in time in which they have the same momentum. So when that's occurring, we want to know what is the ratio of the kinetic energies. Plugging in this relationship, remember that the momentums are the same at this instant of time, and now we want to compare them. Okay, so we don't actually need these subscripts, and these things cancel, and this cancels. And it tells us then that at that moment of time, the ratio of these kinetic energies is equal to the inverse ratio of their masses, so that the kinetic energy of A is going to be less than the kinetic energy of B. I can do the reverse, and I can say, well, what happens when they have the same kinetic energy? And I can derive a relationship based upon the ratio of their masses as well, so that I can conclude that the momentum of A is going to be greater than the momentum of B. So, a good question might be, what happens if these two cars, rather than coming to a stop, what happens if they were to collide with one another? In order to start discussing collisions, I want to introduce another conservation law to you. We've already discussed the conservation of mechanical energy. Now we're ready for the conservation of linear momentum. This conservation law tells us that if the external forces on the system are equal to 0, then the total momentum of the system is going to be conserved or constant. So the change of momentum of the system is going to be equal to 0. So momentum can transfer from one object to another, but this change has to equal 0. So oftentimes we are analyzing the collisions using conservation of momentum. It's one of the classic applications of conservation of momentum. And so when we are discussing collisions, we can define these kind of collisions, or any kind of collision, as being generically some sort of interaction in which two objects interact with one another and emerge with potentially different velocities than what they started with. And we're going to define two broad categories of collision, the first of which is sort of an idealization. So in this first category, we call this an elastic collision. In an elastic collision, we have the condition that not only is the momentum conserved, but the mechanical energy is also conserved. And this is due to the fact that the interaction forces involved are all conservative. On the other end of the spectrum, we have something called an inelastic collision, in which there are non-conservative forces acting as well. And so although the momentum is still conserved, the total mechanical energy is not conserved. Some of that energy goes into heating or sticking the objects together, or even deforming the objects in some way. So the classic example given for an approximately elastic collision is when billiard balls collide with one another, and there's very little in the way of other non-conservative forces at work. For an inelastic collision, one classic example might be a football player tackling another football player, and then they are sticking together as one object with a combined momentum. Okay, we're going to do examples of these collisions in the next lecture, but in the meantime, I would encourage you to check out this video by Physics Girl, in which she analyzes both the energy and momentum involved in what we would call the super bounce of one ball bouncing off of another.